Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors and the Geometry of Space, Section 1, Three-Dimensional Coordinate Systems, Video 5, Equations of Spheres. I should have mentioned this in the first video, but I am using a specific textbook in reference to chapter and section number. The textbook I'm using is Essential Calculus Early Transcendentals by James Stewart, 2nd edition. All right. So what is a sphere? Well, it's a ball, but more specifically, it's the three-dimensional version of what we know as a circle in 2 dimensions. So like before, we're going to go from 2 dimensions to 3 dimensions. So let's review circles. In 2 dimensions, the equation of a circle with center hk and radius r is x minus h quantity squared plus y minus k quantity squared equals r squared. You should know this already. You're in Calculus 3 if you're watching this, or you think you could be in Calculus 3. I have a picture of a generic circle with the generic center, a generic radius, and a generic point on the circle. And the reason I wanted to do that was to point out that you can derive the equation of a circle one of 2 ways. Number 1, you can hit this picture with a distance formula by saying that the distance between hk and xy is equal to r. And then you'll get r equals the square root of some stuff. You square both sides, and you get the equation that you see on the left side of the screen. The other way is to not even use the distance formula, but rather to use the Pythagorean theorem. And if you're wondering, how can I use the Pythagorean theorem? There's no right triangle. That's easy. Make one. Like this. Now, how could that be helpful? Well, to put it simply, the length of the bottom side is x minus h. Now, the nitpicky out there will say, what if x minus h is negative? Well, then it's the absolute value. And the length of the other leg is y minus k. Again, technically, that can come out negative, so it would be the absolute value. But when you square it, it won't matter. And then you just hit the Pythagorean theorem on that triangle. X minus h squared plus y minus k squared equals r squared. Piece of cake. So what about in 3 dimensions for a sphere? Let's think about this before I go to the next page. How would this picture change in 3 dimensions? Well, it would be a sphere instead of a circle, but everything that's labeled with an ordered pair would be labeled with an ordered triple. The ordered triple of the generic point on the sphere surface would be x, y, z, but the generic, the center of the sphere, we have to give a third coordinate. So we're going to call it h comma k comma something. Well, the truth is, it doesn't matter what you call it. But I'm going to be consistent with the book that I'm using for a frame of reference and call the center h comma k comma l, because l comes after k. Well, why did they skip I and j? Well, I is the square root of -1, and j has something to do with linear algebra. And in fact, it's something we're going to see later in this course, later in this chapter, when we talk about our standard basis vectors. But there's a reason I and j are skipped. Come to think of it, along that reasoning, k should be skipped also. But let's not go down that rabbit hole. The equation of a sphere with center HKL, and I'm going to use capital letters so the L doesn't look like a 1, and radius R, looks just like the equation of a circle. The only difference between this equation and the one back here, besides the choice of letters for the center, is that this equation has a third add-in to accommodate for the z coordinate. And for those of you who are already thinking on a higher level, yes, this could be extended to 4-dimensional spheres, 5-dimensional spheres, as many dimensions as you want. Good luck visualizing what that looks like, but it doesn't really matter. And again, we could do the exact same thing. We could just draw the correct triangle, correct right triangle, and hit it with the Pythagorean theorem. The problem with this is that we would need something a little bit more than this, because we would need to make sure that the sides would be parallel to the x or the y-axis or the z-axis. So really the picture would probably look something a little bit more like this. Go this distance in the x direction, this distance in the y direction, and then this distance in the z direction. Now, is there a 3-dimensional Pythagorean theorem? Yes, but we could also just use the distance formula and square both sides. All right, so it's just like the equation of a circle. There's just a third part to account for the z-coordinate, both of the generic point on the surface of the sphere and the z-coordinate of the radius. Now, I'm not going to do easy peasy college algebra questions like give you an equation that looks just like this, ask you the center and the radius, or give you a center and radius and ask you to build an equation that looks like this. So what level am I going to demonstrate? Well, a level that is sometimes skipped in college algebra for various reasons. But what if you have an equation? Oh, I'm sorry, I forgot. I'm getting ahead of myself. Before we get to the example, if the center of your sphere is the origin, then the equation collapses down to x squared plus y squared plus z squared equals r squared. This equation that you're looking at right now is critical when we get to triple integrals in spherical and cylindrical coordinates, more spherical than cylindrical. But that's down the road, so don't sweat it right now. It's like chapter 12. But note that this is a sphere centered at the origin. Now let's get to an example. Find the center and the radius of a sphere whose equation is x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 5 is equal to 0. It's like, whoa, what's going on here? All you've shown me is this, and you're asking me to do that. Well, yeah, big deal. In theory, this is a skill that you've seen before, but may not have practiced in a while, so we're going to go over it. We're going to have to do some completing the square, and then we're going to sketch the sphere and find its volume. My OCD will not let this slide. There, sketch the sphere and find its volume. So we got an obstacle to overcome. And I want to focus on a problem-solving strategy that I teach in my lower level classes and reinforce in my upper level classes. How do you take something that you don't know how to do and turn it into something you do know how to do? And the answer is by figuring out why it's different and then fixing that. Why is this equation different than this one? There's a lot of right answers to that. Well, this equation contains parentheses, and this one doesn't. This equation contains x squared and x, y squared and y, z squared and z. This one doesn't. This one only has an x, or x squared if you look at it as a squared parentheses. So if we can take this equation and make it have the same structure as this equation, then we can extract the center and the radius and do what we need to do. Now, how are we going to do that? By fixing what's wrong with it. This has too many letters. This has x, y, and z in two different places. This only has x, y, and z once. So how do we fix that? Well, we're going to have to complete the square, meaning that we got to find the correct constants to turn the x's into a perfect square trinomial that factors. Just to give you a sneak peek before I get to the next page, look at just the x's for a second. X squared plus 4x. It would be nice if I had a number here that would cause this to factor into something squared. Because if I can do that, then it's going to help me attain the form that I want and pull out the information that we need, the center and the radius. So how do we get from here to here? Well, it's a story that I've told before in college algebra. I've got a college algebra video that really motivates how to complete the square, but this isn't the time to reteach all of that. I'm just going to remind you how to do it, though. And so we must complete the square to rewrite the equation in standard form. Standard form is what I mean for this equation. Standard is such a weak adjective. There's also a general form. What you see here is standard form. What you see here is general form. Both adjectives are very weak. But regardless, we got to make this thing look like that thing. And the move that will do it is completing the square. So how do we do that? Well, the first thing we do is we rearrange the terms in the equation by variable, and we move the constant term to the right side. The constant term is the term that doesn't have a variable. In this case, the constant term is plus 5, so we're going to subtract it over to the other side. And while we're doing that, we're going to rearrange these pieces. X squared plus 4x. And I'm going to leave a space here because what I want to try to do is to create a perfect square trinomial. And let's gather the y terms. Plus y squared minus 6y. And again, we're going to leave a space to complete the square on the y's. And it will always be a plus, by the way. You'll see why in a moment. And then the z terms. Z squared plus 2z plus some unknown constant, and then we need that to equal, well, it's going to equal -5 for now, but that -5 is going to change also. Now, how do you complete the square? Well, I'm just going to review it real quick because if you need help, I got a video. Go to my YouTube channel. You may be there already. Go into my playlist, find the one that says College Algebra, Math 1314. Find the video from section 1.5 point something, and it will say completing the square. So you can go watch that. But anyway, to complete the square, you have to take the coefficient of the linear term, linear meaning first power, and do two things to it. Cut it in half and then square the result. Half of +4 is +2. +2 squared is +4. That's why it's always a plus, because the last move there is squaring. If we do it on the y's, take the coefficient of the linear term, -6, cut it in half and square it. Half of -6 is -3. -3 squared is +9. And then the same thing with the z's. Take the coefficient of the linear term, the +2, cut it in half and then square it. Half of +2 is +1. +1 squared is 1. So I need a 4, 9, and a 1 in order to factor these into perfect square trinomials. However, I can't just drop a 4, 9, and 1, expect everything to be okay, because this is an equation that's balanced, and whatever I add to one side, I have to add to the other. If I'm going to add 4, 9, and 1 to the left, then I have to add 4, 9, and 1 to the right, and I'm going to write them all on top of each other. +4, +9, +1. Normally, I would write them to the right, but I don't have room over there. Now, what's the consequence of all this? Well, all of the trinomials will factor into something squared. X squared plus 4x plus 4, that factors into x plus 2 squared. Excuse me, let's fix that. That factors into x plus 2 squared. Plus, what about the y squared minus 6y plus 9? That factors into y minus 3 squared. And if you need help factoring, please let me know. I've got videos on that also. Plus, and then the third trinomial, z squared plus 2z plus 1, factors into z plus 1 squared. I want to make a quick comment about all three of these factorizations. The numbers that show up in the parentheses are what you get after taking half of the coefficients we did. Like when we took half of the 4 and squared it in the first highlighted yellow part, half of +4 is +2, and notice that +2 is what shows up right here. In the middle one, we took half of -6 and then squared it, but half of -6 was -3, which shows up in the factorization. And on the third one, half of +2 is +1, which showed up in the factorization. Now we got to clean up the right side of the equation also. -5 plus 4 plus 9 plus 1 is +9. So we have our equation, but we haven't answered any questions yet. We haven't found the center, the radius, the sketch of the sphere, or find its volume. Well, let's move this equation to the next page. X plus 2 squared plus y minus 3 squared plus z plus 1 squared. Also, another thing I didn't mention in a previous video, but when I draw my z's, I will always put a line through the middle, so you know it's not a 2. So z's always have lines through the middles when I draw them by hand. All right, so let's answer all the questions, starting with the center. What is the center? Well, it's the numbers being subtracted in each parentheses. Be careful. The center is not 2, -3, 1, because that's not what's being subtracted. What's being subtracted is -2, 3, and -1. Or in a nutshell, when the center goes in and out of the equation, you change the signs of the numbers. Notice here in the yellow part, the H, the K, and the L look negative. When I write the center, they look positive. I say look because I don't know, they could be negative or positive already, depending on what they equal. But when the center goes in and out of the equation, the numbers change signs. So if it's minus in the parentheses, it's plus when you take it out. If it's plus in the parentheses, it's minus when you take it out. So the 2 comes out as a -2. The -3 comes out as a 3. And the +1 comes out as a -1. Now, what's the radius? Hint, it's not 9, because the 9 represents the square of the radius, and so to get the radius, we'd have to take the square root of 9 and get 3. All right. Can we sketch this? Of course we can. I'm going to do my best to show you how I would sketch this, but let's go ahead and figure out did I say area? No, I said volume. Right here, I said volume. Now, if you don't know the formula for the volume of the sphere, I understand it's not a formula that you use all the time, but it's also past knowledge, and you're expected to know a lot of things, including the formula for the volume of a sphere. If you don't know it, the formula for the volume of a sphere is 4/3 pi r cubed. You can actually prove that by taking a semicircle in the XY plane, generic semicircle centered at the origin with radius r, rotated around the XY axis and find the volume using the disk method. I invite you to try that, former Calculus 2 students. But our radius is 3, so it's 4/3 pi times 3 cubed. Well, the 3 in the denominator would cancel one of the 3's in the 3 cubed, so it's 4 pi times 3 squared. 3 squared is 9. 9 times 4 is 36. And we got a pi, so our volume is 36 pi. Now, as far as sketching this, let me show you how I would sketch it. Oops, I thought I had a 3D coordinate space set up. 1 second, folks. Okay, I set up an X, Y, and Z axis, and I have them marked as far as I do for reasons which will become evident in just a moment. But I want to start by using traces to locate the center, meaning that we start by going in -2 in the X direction, which will be -2 backwards along the X axis. I want that to be a thicker line. So let's try this. And then I want to go 3 in the Y direction. Well, from the origin, 3 in the Y direction is 3 over here. But let me translate that to where I left off after the X trace. And then -1 in the Z direction is 1 down. So let's go 1 down from there. So our center is going to be right about, come on, let me draw a circle, please. Our center is going to be right about here. Now, how can we locate this sphere now that we know where the center is? I'm going to shift to brown, and our radius is 3, so we need to go 3 in each direction. Let's start with 3 in the Y direction. Whoa, that's not what I wanted to do. Let's go with 3 in the Y direction. So I'm going to do 3 in the Y direction, and I'm going to translate it here. And I'm going to do 3 in the Y direction again, and I'm going to translate it here. Now let's do 3 in the Z direction. So Z direction 3, I'm going to move it here. And then Z direction 3. And I'm going to put some points on these, the endpoints of these brown segments. So let's put them here, a point here. Now we can find the coordinates of these points fairly easily by simply adding and subtracting 3 from both the Y and the Z coordinates. Notice I haven't touched the X coordinates yet. So for example, this one on the left, excuse me, this one on the right is 3 in the positive Y direction from the center. So instead of being -2, 3, -1, it went 3 in the positive Y direction. So this would be 6. Or this one down here, the center was at -2, 3, -1, and we went 3 in the negative Z direction. So our Z would go down by 3 and become -4. And I'm going to draw a circle that goes through these 4 points. Let's see if I can nail this. Let's see. That's not too terribly bad. I could freehand it. And now I'm going to get rid of the segments in the middle. I just use those as guides to find those points. Get rid of that. Get rid of that. Get rid of that. Get rid of that. Now, what about the in the X direction? Well, let's just go forwards and backwards in the X direction. And again, the radius is 3, so I'm still going 3 in the X direction, which is marked as 1, 2, 3. And let's put that from here. Okay, well, this isn't turning out exactly how I wanted it to. That should not have hit that exactly. Okay, these scales on the axes are not well drawn to scale. Okay, that didn't quite turn out the way I wanted because I didn't know I was going to hit it there. But let me show you what I would normally do. I'm more concerned about the YZ directions because those are up, down, left to right like we're normal to. The third dimension, or the one coming off the page, the X, is a little bit trickier to draw. So what I would normally do is the up, down, left, right, which are the the positive, negative X's, excuse me, positive, negative Y directions and positive, negative Z directions. So in the center, but then to get a 3D flavor for it, I would just kind of hand draw a little arc here. And if you really want to give it some depth, do a dotted one in the back. Just make sure I know what your center and your radius is. It's not necessary to label these points here. I just did those as a guide to help me draw it. All right, so I think I've shown you the most difficult thing that I'm going to ask you to do with spheres, at least right now. There's a little bit more we're going to do with it in the next video. But if completing the square was throwing you for a loop, let me know and I'll hook you up with a good video, or you could just search, you know what? We're on the internet, or we're about to be on the internet. Here, let's just go find them. I have no idea what might pop up. I don't know what I've been watching on YouTube. Probably poker or something. Yeah, I hate stupid stuff like this. But yeah, I love Kill Bill though. I'm going to my channel just to show you where to find this. You could just search. Let's just put completing the square and see what pops up. No. Here we go, solving the square, solving by completing the square part 1. And I'm pretty sure this video introduces the concept and why it works. But if you need some practice completing the square, go to my YouTube channel, search completing the square, and I would watch this part 1 video. Actually, I got a couple of options here. Oops, I wouldn't do any of the part 2s because who knows what I said. But anyway, you guys can use the internet. You don't need me. Well, maybe you need me for calculus, but you don't need me to show you how to find things on the internet. Come on, stop recording. Thank you.